Howdy folks, in our next two videos we're going to take a good hard look at the linking and unlinking of sugar molecules to make and destroy complex carbohydrates. We're also going to get an idea of how geometry plays into this and shape plays into this, and why it is that there are certain sugars, certain complex sugars that we can digest and others that we can't. To the worksheet.
Here's a pretty typical disaccharide, and what we're going to do with it is the same thing that our body would do with it if we ate it, and that is to hydrolyze it immediately. Turn it into two simpler sugars that are easier to bring into the metabolic processes that we will study in Chapter 12. Remember that hydrolysis only works for certain functional groups. We learned that we could do it with amides, we could do it with esters, we could do it with phosphoesters, and we could do it with the specific kind of ether that you find in a sugar. And so what we're going to do is break this ether group here that is making up what we call a glycosidic linkage. In other words, a linkage between a pair of sugars. Note that gluco, glyco, that prefix tends to refer to sugars. Remember with ethers that it really didn't matter which side of this we did the split on, so I'm just going to pick one. We'll go ahead and split right there. The key thing was when we hydrolyze something, what we're doing is adding water to it. That addition of water comes in the form of an H and an OH. And the thing we did have to remember was where those each go. Crucially, that the OH goes onto a carbon and the H is going to go onto an oxygen. And so that's where these are going to add to either side of this bond. We're going to downgrade the single bond to nothing, and we're going to wind up with our product. And if I examine this side right here, I'll see that over here the OH should be down where I'm creating it, as should be the case on the other side. And it's also worth noting that all of the OHs are in the same places on these two individual sugars. It goes down, down, up, down, up, down, down, up, down, up. So what I actually am going to have are two of the same sugar. And crucially, I'll have the OH down on that side like I see right here. Everything else I'm just going to write from the structures. What we've actually generated here are just simply two glucose molecules. And so what maltose turns out to be is a dimer of glucose. Now, because we have so many options when we link together two sugars or three or four or several thousand sugars to make a disaccharide, oligosaccharide, or polysaccharide, I want to be specific about which carbons were involved in making the glycosidic linkage. And so that's what I mean when I say classify the linkage. Now, in practice, most of the time, the anomeric carbon of at least one of the sugars is involved. And I want to show you briefly the easy way to find the anomeric carbon in something is that it's always the only carbon in a ring that's bound to two oxygens. Because notice it was bound originally to the O from the aldehyde, or ketone, depending on what kind of sugar it was, and then it also ends up bound to the O that wrapped around to complete the ring. So it would be the same carbon in both situations here. And so notice this is the anomeric carbon for my first sugar. And because there's nothing else attached here, that actually means that this is carbon 1. So I'd have 1, 2, 3, 4, 5, 6. We're dealing with glucose, which is an aldose sugar, so the anomeric carbon will be carbon number 1 in that case. As for the other one, 1, 2, 3, 4, 5, 6, I'll see here that carbon 4 is involved on the other side. So initially, I can just call this a 1 to 4 linkage. But remember, I have to be a little more specific than that, because this OH could have pointed in either direction. What we'll see is that right now the OH is pointing down, the CH2OH outside the ring is pointing up, and remember that trans configuration means I'm dealing with the alpha anomer. So wherever I have an anomeric carbon, I need to specify which configuration it's in. So that'll be the complete way of writing maltose's glycosidic linkage, alpha 1 to 4. Now what maltose kind of resembles is baby starch. Because if I just do that over and over and over again and use this alpha 1 to 4 linkage, eventually what I wind up with is a long starch molecule, namely the straight chain version of it, known as amylose. This is one of the two major components of starch. The other one is called amylopectin. And the big difference between amylopectin and amylose is the presence of some branching. Whereas amylose is just this 1-to-4 linkage over and over again, we add branches by way of an alpha 1-to-6 linkage to make amylopectin. Now, what I'd like you to do is point at, on this second sugar in the chain, point at carbon number 6, because you'll notice that carbon number 1 is used up in all of these. So I'm going to bring in a new sugar molecule to make the branch. It's going to use its carbon number 1 in order to form it. So we'll have to use carbon number 6 from the chain that already exists. Find carbon 6 on this sugar right here. Okay, now that you've taken the time to do that, I hope you found that it's right there. Again, carbon 1 would be my anomeric carbon, note bound to 2 oxygens. Carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So to make my branch, I'm going to attach a new glucose monomer right here. Now to do that, of course, I'm going to begin by making my ring. I'm going to place everything where it belongs. It's still an alpha 1-to-6 linkage, so I'll go ahead and put the OH facing this way. The other ones all go where they need to because it's glucose, so we'll see on the structures above, down, up, down, and the CH2OH there. Now, remember, this is going to start off having an H in this spot, but in order to condense, I'm going to do the opposite of hydrolysis. I need to remove an H from one atom and an OH from another atom in order to generate excuse me, a new bond between them. And I think the easiest way for us to do that is to grab the H from here and the OH from there. And if those both leave as a water molecule, the result will be a new bond between those two. And that now gives me my 1-to-6 linkage. Notice now that it is carbon 1 in the alpha position bound to carbon 6 of this. And of course, if this was truly an amylopectin, I would now start making 1-to-4 linkages going off in that direction, also ad nauseum. Now, the only difference between this polysaccharide, amylopectin, and another one you may have heard of called glycogen, this is animal starch stored in your muscle cells as a reserve to make extra quick glucose if you run out of what's in your bloodstream. The only difference between those is specifically how much branching is going on, how frequently they occur. Amylopectin, we're talking about one of these branch-off points roughly every 12 to 15 glucose molecules. In glycogen, it's closer to once every 6, a much more heavily branched structure to contain a lot of glucose in a very small amount of space. In our next video, we're going to look at some beta linkages and get a bit more practice at classifying these things.